Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today we're going to continue the lecture from last time where we talked about multiple integrals. In fact, we're going to do more general regions today. So if you recall, the last lecture we talked about doing double integrals over rectangular regions. Today we'll consider more general regions. Okay, so the idea is we want to be able to integrate over non-rectangular regions as well. And so we'll consider two types of general regions that are non-rectangular. Okay. Type 1 region, well, that's a region bounded by two continuous functions of x, right? So a region bounded by two continuous functions of x, all right? So for example, how would this look pictorially? So there's the xy plane. Maybe you have those two functions. You want to integrate over that region, right? So your x limits are constant, right? There's some constant a and b x limits. And your y limits, well, not y1, but y is some function of x for the bottom function, and y is some function of x for the top function. So you have two continuous functions of x, g1 and g2, and your x limits are constant here, right? So here, the region is, well, x lies between a and b, and y lies between these two continuous functions. That should be a 2 there, shouldn't it? These two continuous functions of x, okay? And so since we have y being a function of x, we're going to integrate first with respect to y to get rid of all the y's, then we'll integrate with respect to that. So since y is a function of x, right, our plan is integrate with respect to y to get rid of the y's, then do the x's, right? So integrate first with respect, WRT, with respect to y, then with respect to x, right? So integrate first with respect to y, then with respect to x. So where do I want to put this? So for any type 1 region, how does the integral look? Well, we'll call this region D, right? So this is just D there, right? So the integral, or the double integral over D is the double integral, the function f of xy dA, right? Integrating with respect to y first, x second. So g1x, g2x, right? F of xy, respect to y first, then respect to x, right? So we're integrating from the lower limit of integration with respect to y here to the upper limit, right? And then the lower limit with x to the upper limit of x. So lower limit, upper limit, respect to y first, respect to x second. Okay? Okay. So that's the first kind of region. Let's get rid of this. So we'll just call the next one, it's a type 2 region. And honestly here, everything sort of follows suit. The only difference is we're considering now functions of y. So I'm erasing all this. Basically, we're going to have a few changes along the way, but the same idea is going to apply. So now we have a region bounded by continuous functions of y, okay? So, e.g., there's the xy plane. Now maybe your region looks like that. So there's your region D in there, right, between those two curves. And so now it's your y values that are fixed constants, C and D, right? And then this curve over here is some function of y, and this curve over here is also some function of y, right? So there's one function of y, and I'll even outline it in red to make it look nicer. So there's one function of y, there's the other function of y, okay? And so here, our region is, well, we've got c less than or equal to y less than or equal to d, and h1 of y less than or equal to x less than or equal to h2 of y, where we're integrating left to right. So we're integrating left to right here, so we're proceeding like that. We integrated up to down before, left to right here, okay? And so here, x is a function of y, so we're going to integrate first with respect to x to get rid of that, right? And then integrate with respect to y, okay? So your double integral of d, or over d, of f of xy dA, right? Integrate with respect to x first and respect to y. So we have, there's our y limits, our x limits. Again, they proceed left to right in this case, right? F of xy dx dy. What I have here? Yeah, good. So y limits, x limits, x first, y second. Okay, so those are your two types of regions. Well, the fact is that lots of regions can be expressed both ways as a type 1 or type 2 region. And that's fine, but it may be the fact that one way or the other of looking at things leads to easier math. So many regions can be expressed both ways. But as we all know, unlike taking derivatives, doing integrals can be very hard depending on what the functions you're integrating are. So it may be that expressing it one way or another leads to an easier integration. Okay, so one way may be easier to integrate. And of course, both ways will give you the same answer because they're the same region, right? So let's take a look at one here. Let's evaluate double integral of d x plus 2y, and let's have d be the region bounded by, what am I doing here, parabolas y equals x squared, I'm sorry, y equals 2x squared is what I wanted. So y equals 2x squared and y equals 1 plus x squared. Okay, the region I want to integrate over. So first things first, we'll draw a picture of what's going on here. Maybe we'll make this, well, maybe not yet. So 2x squared, well, probably looks something like that. Maybe there's 2x squared. And then x squared plus 1 is a little bit wider than 2x squared. Maybe it looks something like that, and it's moved up 1. So what we want, so there's some intersection points. We want that region right there, right? Well, that's certainly not rectangular, so we're going to have to use our ideas of what we have in this section with the general regions. Okay, So we need the limits of integration is the first thing we need. And actually, it's worth noting, too, that we are expressing, or the way I've drawn this here, you can look at it either way. You can consider this to be upper and lower functions of x, or you can consider it to be right and left functions of y. We'll look at it as a type 1 region. So maybe I want to use green there, show it off. So we're considering the integration to be proceeding that direction. So the green curve is your lower limit curve, and the orange curve is your upper limit curve. Okay? So for limits of integration, right? Well, the x values, we want them to be constants. In particular, we want them to be this value there and that value there, right? That's where the x limits are, so we need to figure out where the two parabolas cross, right? Those two crossing points. So we want values where the two parabolas cross. That means that 1 plus x squared equals 2x squared. Let's see, what do you do with that? You fiddle around with some stuff, and you get x squared equals 1. So x is plus or minus 1. Okay. So there's the x limits of integration. So -1 is less than or equal to x is less than or equal to 1. For the y limits, we want the lower curve to be the lower limit and the upper curve to be the upper limit. So we want, so the lower curve is 2x squared. The upper curve is 1 plus x squared, right? And so these two inequalities taken together, right, these are D. So those two inequalities together form the region D that we're integrating over. Okay? So let's go ahead and do this. So let me erase the picture up here, and we'll do the computation. So there's the region. Right? Let's get rid of that. Okay? So we have our region D, and so we have this double integral over the region D of x plus 2y dA, right? We're doing this as a type 1 region, so we integrate with respect to y first, then respect to x. So x limits are -1 to 1, y limits 2x squared, 1 plus x squared, dy dx as such, right? Okay, so integrate with respect to y first, so we leave the x stuff alone. Let's see here. So x is treated like a constant, so this ends up being xy. 2y, the integral of that is 1/2, I'm sorry, it's y squared, excuse me, y squared, right? And then the limits here are y equals 2x squared and y equals 1 plus x squared. And we still have this dx hanging around out there, right? Is that what I got? Good, 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 yeah. All right, and then you integrate. So you do all this junk out here. Do I want to actually do it out? Maybe. Do I do it out here? Yeah, I do. Okay, so let's go ahead and do it out. So let's see, plug in these limits of integration. So you have x times 1 plus x squared plus 1 plus x squared minus 2x cubed. And oops, I forget to get the squared there. I did, didn't I? Yeah, the squared on that. And then let's see, this would be plus what, 4x to the fourth, plus 4x to the fourth. And then that would all be in terms of, so that whole thing in terms of dx. Look right there to me. Yeah, it looks good, looks good. Okay. So if you do all that out, what in the world do you get? Integral of -1 to 1. Let's see. So if you combine all this up, in theory, this is all right. You get -3x to the fourth minus x cubed plus 2x squared plus x plus 1. All right. So if you combine all that up, that's what you get. So you have this thing in terms of x now. All right. And so if you go ahead and crank that out, what in the world do you get here? You get -3/5 x to the fifth, and then -1/4 x to the fourth, and plus 2/3 x cubed, and plus 1/2 x squared plus x integrated from -1 to +1. Make sure I have everything there. Looks good, looks good. Yep, looks good. All right, and if you do all that out, you get 32/15. Okay, so there's your value of your integral. So we integrate with respect to y first, then x. Okay, let's do another one. So that wasn't too bad. Sometimes the hardest part is drawing the region and seeing what's going on with that. Once you have those limits of integration, the process is usually pretty simple as long as your functions are easily integrable. They're elementary functions. So let's try one here with volume. We talked about how volume is related to integrals last time, or double integrals. So let's find the volume of the solid that lies under the paraboloid z equals x squared plus y squared, and above, oops, shouldn't be an R there, above the region D. What's our region D here? In the xy plane. Let's have D be bounded by the line y equals 2x and the parabola y equals x squared. Okay? So I want to find the volume of the solid. Well, we know that finding the volume of the solid means integrating this function over the region that we are told we are restricted to. Okay? So again, this is one of those where you can interpret either as a type 1 or a type 2. So let's take a look at this a minute. So let's do it as a type 1 first. So let's see here. So y equals 2x maybe looks like that. And y equals x squared maybe looks like that, right? So we want this orange shaded region in there. That's our region D. And in particular, we're going to look at this as type 1. So consider this as type 1. So we're sort of going from top to bottom like that. And so our upper curve is y equals 2x. Our lower curve is y equals x squared, like that, all right? Okay. And so what are our limits of integration? Well, for the x values, so where is 2x equal to x squared, right? So what do we get? We get x squared minus 2x equals 0, and you pull out an x, and you get x minus 2 equals 0, and you get x equals 0 or x equals 2. Look right to me here. Does it look good? Yeah, it looks right. So there's 0, and there, that point up there is 2, right? Okay. So there's your x limits of integration. And your y limits, again, depend on which curve is the lower curve, which one's the upper curve. So our y limits are stuck between x squared less than or equal to y less than or equal to 2x. That's our region D, right? So there's the region considered as a type 1 region, okay? So our integral then, double integral of D, x squared plus y squared. Again, if we integrate the function of the surface's height, we will get the volume. And we're going to do y first, then x. Oops, didn't mean to do that. So the x limits of integration go on the outside. Y limits go on the inside. 2x, x squared plus y squared dy dx. There is the double integral we're going to deal with to find the volume. Right? Okay? So I will do this shortly, but let's express it as a type 2 region first. So here's the type 1 region expression. All right? Here's the limits. Here's the integral you get. Okay? Let's try this as a type 2 region. So let's dump this. And again, they will give you the same values. There's no difference there. Maybe one is easier to do than the other. So let's see, type 2. All right? I shouldn't have erased my picture. Well, I guess it's okay. So it's the same line, right? Same parabola, right? It's the same region, so we're doing exactly the same thing, only this time we're considering it to be a left to right movement. So now we're looking at our integration going that direction, right? And this time we're considering in terms of y, right? So the line now is y equals 1/2 x, right? Or I'm sorry, excuse me. Oops, that's not true. It's actually x equals 1/2 y. X equals 1/2 y, because y equals 2x turns into x equals 1/2 y, right? And then the orange curve becomes x equals the square root of y, right? Because y equals x squared implies x is equal to plus or minus square root of y. We only have positive numbers here, so we don't need the minus, so we can just have x equals square root of y there, right? Okay, so our limits now, so we have what? 1/2 y equals square root of y. We want to get our y limits, so we can square both sides, get 1/4 y squared equals y, right? And scoot things around that way, minus y equals 0. Pluck out a y, you get 1/4 y minus 1 equals 0. So y is equal to 0, or y is equal to 4, right? Does that sound right to me? Yes, it does, yeah. So there's our y value of 0, right? Here's our y value of 4, right? Okay, so y is stuck between 0 and 4, and the x curves go from left to right here. So we have what, 1/2 y less than or equal to x less than or equal to square root y. And that's our region D as a type 2 region, okay? So the integral in this case, double integral over D of, what was my function? X squared plus y squared dA, right? This time we're doing x integration first, then y, so y limits come first, then x limits, so 1/2 y, square root of y, x squared plus y squared, dx dy. So that is the double integral we'd use if this was a type 2 region. Okay? So, all right. Let's go ahead and do one of these. This one's up here. We'll go ahead and do this one. So let's evaluate that. So let's get rid of some of this stuff and give ourselves some room to work. All right. So once the region's drawn, it's just a matter of integrating. And again, if you sort of try one way and it leads you down the dark alleys of not being able to finish the problem, maybe try the other way. So start up here with this double integral, 1/2 y root y x squared plus y squared dx dy. Okay. All right, so respect to x first, so y limits stay the same. Let's see here, so integrating that, so that would be 1/3 x cubed, and then y squared is like a constant, so that's plus y squared x, and that is from x equals square root y to x equals 1/2 y, and that is in terms of dy still, right? Yeah. So let's see here. What do I want to do with this? I guess we'll fiddle around with it. So this winds up giving you 0 to 4. You plug in square root y here, you get what, 1/3 y to the 3/2 plus what? Let's see, y squared times y to the 1/2 is y to the 5/2. And then minus, let's see, so 1/2 y cubed is 1/8 y cubed. That's 1/24 y cubed. And let's see, so that would be, plug in 1/2 here. So 1/2 y cubed is what you would wind up with. And that would all be in terms of dy. Is that what I've got here? Sure, I'm not making a lot of mistakes here. Yeah, looks good, yeah, okay. So integrate that with respect to y, take those limits. So what on earth do you want here? So you want 2/5, so you wind up with 2/15 y to the 5/2. All right, is that looking good? Yeah, okay, it looks right, yeah. And then, let's see, so you want plus 2/7 y to the 7/2, right? And what? So you want 1/4 there, so 24 times 4 is 96, 1/96 y to the 4th. And let's see here, and then 1/8, well, actually that should be a minus 1/8 y to the 4th, all integrated from y equals 0 to y equals 4. Make sure everything is going properly here, so do we look like we're in decent shape? Yeah, things look good. All right, so you plug all that stuff in, what in the world do you get? 216/35 is the volume of the paraboloid z equals x squared plus y squared over the region D. Okay, so there's your answer out of all that. And had you done this backwards, so had you gone ahead and done the integral from, 0 to 2, and then which one was top and bottom? X squared to 2x of x squared plus y squared, and had you done dy dx, had you written this as a type 1 region and done the integration like that, you would have gotten the exact same answer. Okay, so you would have gotten the exact same answer no matter which way you wrote the region as. Okay, all right, so that shows you that you could certainly do it either way. And I think honestly, if you did it this way, you wouldn't have any real serious problems. Sometimes, though, you do have problems. Sometimes you find yourself trapped going down one way or the other. And so in that case, you turn to the other integration. So let's show how that can happen. So let's try one here where one way is just not going to work. So let's evaluate integral from 0 to 1 and x to 1 of sine of y squared dy dx. And so let's go ahead and draw a picture here of what's happening with the region before we do anything else. So what does the region look like? Well, the y limits of integration are from the function y equals x to the function y equals 1. So y equals 1 is just that horizontal line. Y equals x is that 45-degree line. Right? So this is y equals 1. This is y equals x. They want these limits or they want this region right here, right? And we're calling this a type 1 region, so we're proceeding up like that, right? Okay. So that's no big issue there, and we can see that the x-limits integration here are certainly 0 to 1. But the problem is integrating sine y squared. So the integral sine y squared dy, well, this is not an easily integrable function. And so, what are you going to do about it? Nothing. You're not going to figure it out, right? So we're sort of jammed going this way, okay? So I should say use an integral function with respect to y. I should say that. With respect to y. Now, if it was respect to x, well, this whole thing is just a constant, so that's really nice there. So let's try to reverse these limits of integration, because if we get this with respect to x, this is just a constant here, okay? So let's go ahead and reverse these. So let me erase my arrow in there, and instead of doing this, let's erase this too, let's erase the curves. So instead of going the direction we went before from top to bottom, let's go left to right, right? So let's make this a type 2 region. Let's make this a type 2 region, right? And if that's the case, so what are our limits of integration over here? So that's what? X equals y, right? And this over here is the vertical line, x equals 0, right? So those are our limits of integration there, right? So this integral and our y limits are still going to be 0 to 1. That should make some sense. So we're still going to have 0 to 1 out here with the y limits, but now we're going to go from 0 to y like that. That's going to be our x limits of integration. So we're going to have sine y squared dx dy. That's the important thing, dx dy, right? This is totally equivalent to this. Whatever the answer is here, same answer up there, right? And so now, this is a lot easier because now look at what happens. The y limits stay the same. This is a constant in terms of x, right? So we just get sine y squared x, right? As x ranges from 0 to y. There's a dy there, right? Okay, so the integral 0 to 1. Let's see here. So we're plugging in for x. You plug in 0, the whole thing goes out. You plug in y, you get y sine y squared, right? And so let's see here. What am I doing here? The dy, right? Is that right? Y sine squared, is that what I have here? Where am I? Yeah, it looks good. Okay, yeah. Okay, here we go. Yeah, now we're getting somewhere. So now this is much better because we can use substitution here, right? The addition of this y out front is crucial to doing this integral, all right? So if we use substitution, right? And we can let u equal y squared. So then du is 2y dy, right? And remember this old trick. And so 1/2 du is equal to y dy, right? So there's your y dy, and that's really nice. So this integral, right? So this is kind of sidebar work there. That's sidebar stuff. So this integral ends up being, what, 0 to 1, and then we've got sine u. We have a 1/2 out here. It doesn't make a difference. Sine u du. Oh, that's really nice, yeah? So I've run out of room. Let me come over here. Here, let's get rid of the region. So you have this integral, right? So now you have 1/2, and then the integral of sine was what? Negative cosine, right? So you have 1/2 times negative cosine u. Well, I guess we can plug back in for, yeah, so negative cosine of u from, let's see here. So what am I doing here? Oh, yeah. So negative cosine y squared, I can plug back in from the limits of integration from y equals 0 to y equals 1, right? All look right to me here. Yes, it does, yes. All right. And so this ends up being what? Negative 1/2, and then you plug in 1 there. So the negative cosine of 1 is just whatever it is. So that's 1/2 times the negative cosine of 1, and then the negative cosine of 0. So cosine of 0 is 1. So negative cosine of that would be minus so negative cosine of 0. So cosine of 0 is 1, so that's a negative 1, that's a plus 1, yeah. All right? So you wind up with what? Negative 1/2 cosine 1 plus 1/2. Is that what I've got? Yeah, it is actually. All right. So there's your integral, or there's your answer, I should say. Right? So, and we see it this way, and the other way we couldn't do it. I mean, we didn't have any chance here with this method, but by converting the region around, everything was fine. Right? So that can happen sometimes. Okay, so a couple properties of double integrals to go over, and these are not so very surprising, but they can come in handy from time to time. So properties of double integrals. All right, excuse me. So let's see here. We get double integral from over d. Well, this is basically analogous to the single integral case when you have the sum or difference of two functions, right? Then it's just the sum or difference of the two double integrals. Right? So the sum or difference, or the integral of the sum or difference is the sum or difference of the integrals. That's the same thing as for single variable case. It's also is the same thing. So if you have a constant times f of xy dA, just use this in the last example, it's just the constant times the double integral. So double integral of a constant times a function is the constant times double integral of the function. So I just used this in the last example when I had the 1/2 hanging around, and then I pulled the 1/2 out. Right, that should make sense. Okay, so those two are pretty familiar to us. The last one could actually be of some use if we have really complicated regions. So suppose we have a region that is neither type 1 or type 2, right? So for example, suppose we had, say, this kind of funky looking region here. So let's draw this in orange. So maybe we had something that looks like it's like that maybe, right? So there's your region D. Well, you're not going to get this into a single region because it's got funkiness going on both the boundaries, the upper and lower, and the left and right boundaries, right? And so you can actually, well, you can break D up. You can break D up into pieces, D1 and D2. In fact, you can break them as many pieces as you want to. I'm breaking it into 2 pieces here, but you can break it into 3 pieces or 4 pieces or whatever you want to do, whatever works for you, where each is either type 1 or type 2. So the idea here is you're taking some funky-looking region and you're partitioning it into mutually exclusive pieces that fit the mold of one of our 2 general types of regions, right? So you want to make sure D1 and D2 do not overlap, otherwise you're going to be counting twice, except on the boundary. So they can certainly share a boundary, they have to, but they don't overlap other places. So for example, I could redraw this down here, and I could chop this up, say, into, well, actually I don't need to redraw it, I'll do it right on the original surface. So I could chop it up into, say, 2 pieces like that, right? And I'll call that D1, right? So then I have something that's bounded by functions of x on top and bottom, and I could call this D2, something that's bounded by functions of y on the sides there, right? So D is the union of D1 and D2. Certainly they make up the whole thing of D, putting them together, right? And D1 is a type 1 region, right? It's bounded on the top and bottom by x functions, and D2 is a type 2 region. It's bounded on the sides by functions of y. And so it should come as no surprise that if we do the double integral, some function over that, well, so it is the double integral over D1. Am I using dA here? I am using dA. I'm not getting any further than that. So it's the double integral of D1 over, or plus the double integral of D2. So if you're breaking a region up, you're just going to sum all the pieces together. that's why these shouldn't overlap, otherwise they would create a repeated values there. Okay? Okay, so let's finish up with a couple applications of double integrals. And so we'll briefly discuss these. And both of these should be pretty familiar to you from single variable integration. All right? Talk about area and average value. So we'll start with area. All right? So the area of a closed, bounded plane region D is, well, it's the integral of 1 dA over d, right? So this should look awfully familiar to you from doing calculations of area from single variable calculus, right? And the reason is the following. So let's make a picture here. So let's say that I have some region D. Where do I want to put this thing? Let's put it down here. All right, so there's my region D, right? And then say I draw it up so that it meets the plane D or Z equals 1. So let's see if we can't make this look reasonably like, I don't know, good enough, all right? So this is the plane Z equals 1, right? Okay, so this is a height of 1. It's a height of 1 for every D value down here, right? And so probably actually keep that looking like that, and then maybe continue it down there, right? So there's your cylinder, right? So this is a cylinder. This is a cylinder with base D and height 1, right? So it has a constant height, right? And, well, its volume, right? Well, we know that whatever the area of D is the area of the base. It's the length and the width, and the height is 1. So the volume is whatever the area of D, A of D, times 1, right, which is A of D. So this is area of D, right? Because that's volume is length times width times height. This is the length times the width, the area of D, and this is going to be the height there, right? Okay. So and also we know that the volume of the volume of a solid under a certain region is integrating over the height of that region over D, right? So this integral here comes from the fact that we are integrating over this height function over this region here, right? So this is one expression for the volume. This is another expression for the volume. That's why they're equal, because they are the same thing got in two different ways, okay? So that's why that formula works. So let's try it out here on one. So let's try to find the area of something that's bounded here. So let's find area of the region enclosed by the parabola y equals x squared and the line y equals x plus 2. Okay? So we'll draw a picture. So x plus 2 maybe looks something like that. Right, there's x plus 2. And the parabola x squared maybe looks something like that. So you've got your region that you want the area of right in there, okay? Right? And let's see here. We'll call this a type 1 region. It looks pretty obviously to be good solid type 1. So we want intersection points for x. We want x plus 2 to equal x squared. So x squared minus x minus 2 equals 0. Leads us to what? X minus 2, x plus 1. So x is 2 and x is negative 1. Okay? So our region for x values is bounded between -1 and 2. Okay? And the y region, well, the top curve is the line, the bottom curve is the parabola. So our y is bounded between x squared and x plus 2, right? So our area integral, right, integrate with respect to y first. So we have -1 to 2 for x limits. The y limits x squared and x plus 2, right? We're integrating 1 with respect first to y with respect to x, right? Everything look good there? Yeah, okay. So x limits stay the same. This is just y integrated from y equals x squared to y equals x plus 2 dx, right? Because the integral of 1 is y. All right, plug that stuff in. You get what? X plus 2 minus x squared. I guess I don't need the brackets yet because I'm not evaluating. And that's with respect to x. Okay. So you take the integral there, and what do you get? You get 1/2 x squared plus 2x and minus 1/3 x cubed, evaluated from x equals -1 to x equals 2. And if you plug all that stuff in, what do you get? 9/2? Yeah, you get 9/2. So there's the area of that curve. And this was very clearly a type 1 region, had a definite top and bottom curve, no problem integrating that way. Okay? All right, so that was area. One other application that's worth looking at very briefly is average value. Again, this should look familiar to you from single variable calculus, so there's not a whole lot of surprise here. I won't derive the formula, but it basically is very intuitive. So the average value of f over d is 1 over the area of d times the double integral f, don't need parentheses there, do we? F dA, right? So there's the formula, okay? So let's find average value of what? F of xy equals x plus 2y over the region D from the previous example. Right, so we use that region we just used. All right. So again, we'll integrate with respect to y first and then x. All right, and this time our function is going to be x plus 2y dy dx. All right, so integral there to there. With respect to y first, gives you an x, gives you an xy. And let's see here, so and that's plus a y squared from y equals x squared to y equals x plus 2. And we still have that old dx hanging around out back, right? Okay, so let's see here. You integrate that, what do you get? So integral from -1 to 2, you get x squared plus 2x. Let's see, and then plus x squared plus 4x plus 4 minus x cubed and minus x to the 4th. In terms of dx, is that everything I got here? Blah, 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 minus x to the 4th, x cubed. 2x squared, yeah, that looks good. 4x, yeah. What happened? Why did I get a 4x there? Yeah, okay, yeah, that's right. So this is going to end up being negative. Let's combine terms here, make everything look clear. So this is going to be minus x to the 4th minus x cubed. Let's see here, you got a plus 2x squared. this should actually be a plus 6x. Thing looks right there, and does it? Yeah, it does, yeah. And then plus 4 with respect to dx. So integrating, what in the world do you get? You get negative 1/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x cubed plus 3x squared plus 4x, all from x equals negative 1, x equals 2. All right, and this gives you something terrible, whatever this gives you. So this is whatever it is. Calculator work will do that for you, but it is what it is. And then you would take that and the area of D. Remember, we found the area of D was what? 9/2. So 1 over 9/2 times whatever this integral is up here, right? And then that'll give you what? 2/9 times the integral of over D for x plus 2y dA, and that'll be your average value. Okay, so that concludes the end of this lengthy section on multiple integrals.